All right, welcome back. So this is our last topic here in Unit 2, higher order derivatives. So everything we've done with the derivative has been finding what's called the first derivative, which, as the name suggests, implies there are more derivatives. So a second derivative is just simply the derivative of the first, third derivative is the derivative of the second, and so on and so forth, as far as I want to go. Now, notation-wise, we use the double prime for f of x, triple prime for the third derivative, and then after that we just do in parentheses the number we want to talk about. So f that 4 means fourth derivative, fn for the nth derivative in general. With our implicit notation, it's d squared y dx squared, d cubed y dx cubed, and so on there, where we're using the number itself as the exponent for that d and the x to indicate the derivative term we're talking about. Now, for the basic power rule situations, we're just doing the derivative multiple times. This can get a little tedious. You will notice after a certain point, if the exponents are positive integers, the expression will eventually disappear and go to 0. So like, for example, here, the first derivative would be a 28x cubed minus 10x plus 6. Whereas the second derivative, now that 6 would disappear. We're going to get an 84x squared minus 10. If I were to go further, you only want the second derivative, so that would be our answer. But if I kind of show what's going to happen if you keep on going when it was a positive integer exponent, the third derivative would be a 168x, the 10 disappears. The fourth derivative would just be a 168, and therefore the fifth derivative would be a 0, and all other derivatives from there. That's a horribly drawn 0. Or written 0, I guess. That's better. All other derivatives after the fifth would also then still be 0. So if it's all positive integers, it will eventually disappear. However, if the exponents are not positive integers, but negative integers or rational numbers, fractions, it will never disappear. Because subtracting by 1 with a negative number just keeps on getting more and more negative. And then fractions subtracting by 1 will never go to 0. They just go to other fractions, eventually negative fractions. So if you're given an expression with the radicals or with the variable in the denominator, again, you got to remember to rewrite them. So f of x is to be 5x to the 1/3 plus 3x to the negative 4th plus 4x to the negative 5th. And we want to find the fourth derivative. So our first would be 5/3 x to the negative 2/3 minus 12x to the negative 5th minus 20x to the negative 6th. And then our second derivative, multiplying again exponent by the coefficient, we get a negative 10/9, x to the negative 5/3 plus 60x to the negative 6th plus 120x to the negative 7th. Our third derivative, we then get a positive 50 over 27, x to the negative 8/3 minus 360x to the negative 7th minus 840x to the negative 8th. Again, each and every time, all we're doing is the power rule derivative. Coefficient multiplied by the original exponent. That's how we got the 50 over 27, the negative 360, and the negative 840. And then the original exponent subtracting by 1. That's how we got the negative 8/3, the negative 7, and the negative 8. And then our fourth derivative, our last one. So again, once again, multiplying 50 over 27 by negative 8/3, we get negative 400 over 81. X to the negative 11/3, we subtract by 1. We get a positive 2,520, x to the negative 8th. And then a positive 6,720, x to the negative 9th. That would be our fourth derivative. Now, most problems in calculus, you're going to only really need to go to the second derivative. It has actual real-world applications. Classic example of stuff like that, your position function is the regular function, the derivative of position is the velocity function, and derivative velocity is the acceleration function. So if you've taken like a physics class or you've talked about that kind of stuff, you should recognize those terms. So most things only really go as far as a second derivative in real-world scenarios. There is technically a derivative of the acceleration function, because we do want to talk about how the acceleration changes. So that's what's called the jerk function. So that would technically be a third derivative term. I only ever really remember dealing with it in college-based classes. So it's never a part of like a high school kind of curriculum, but I haven't been in a high school physics class in many years, so I have no idea. But regardless, if they want you to find multiple derivatives, you just keep on going. This can get a little tedious, more so than this, if there were product rules going on or quotient rules. That gets a little much more obnoxious. In most of those cases, it typically sticks with just the first or the second derivative. Or if you're doing something like the AP Calculus test, sometimes if they want to find, like, the fifth derivative of something, they'll have you start with the fourth derivative. Or if they want you to do multiple derivatives, like a second derivative kind of analysis, which you'll use in real-world scenarios, but it's a crazy complex equation, they'll purposely give you the first derivative to start. That we're only doing one derivative rather than doing two to get to that. Now, we can also use it with our implicit. So we talked about implicit last time in 2.7, so we just go ahead and take our derivative implicitly. X squared becomes 2x, negative 4y squared is 8y dy dx, and the 3 is a 0. So we go ahead and solve for dy dx by subtracting the 2x over. Dividing by the negative 8y to get dy dx equals a x over 4y when we reduce it. And that's where we need to go. We got to make sure dy dx is isolated to be able to find the second derivative of it. Because now, dy dx becomes d squared y dx squared, and now it's a quotient rule. What's our low, d high, minus our high, d low, all over low, low. So we get a 4y minus 4x dy dx over 16y squared. Now, we're not done there. We can't leave it like that because we know dy dx is x over 4y, so we're going to substitute that into the expression. So 4y minus 4x times x over 4y. You'll find in this case the 4's cancel. Kind of nice. The y doesn't, so you're still a fraction there. So it's 4y minus x squared over y over 16y squared. And then, well, we can't leave it in this format either. I've got a fraction within a fraction. So if I multiply everything top and bottom by y, we get 4y squared minus x squared over 16y cubed. And for a lot of questions, you'd be done right there. But sometimes, particularly when there's a both squared terms for the x squared and y squared term, you should notice something. This numerator, 4y minus x squared, is just the opposite of what we wrote here, x squared minus 4y squared. So in fact, if I were to take the original x squared minus 4y squared equals 3, multiply the whole thing by negative 1, we get 4y squared minus x squared and equals negative 3. So my final answer really should be negative 3 over the 16y cubed. That's the fully simplified version of the answer. That's what I'll be looking for our class if you have that kind of expression to rewrite that. Now, that's not going to always happen. If it's like an x with the y squared for our implicits, odds are the numerator is not going to kind of match up like that. If it was like an x cubed with our y squared, odds are, again, it's not going to match up like that. It typically only matches when they're both squared terms. And it might not be an exact match like this one right here, which wasn't exact, it was a negative of it, so negative 3. We might find a scenario where instead we get 12y squared minus 3x squared. So we recognize that's just simply the original times negative 3. So then we can say, oh, it's really going to be a negative 9 up top then because it's negative 3 times the original value of 3. So just look for how the numerator in the final result could relate back to the original equation. If there's a way that they can match, and it should be relatively straightforward to see it, then you want to go with that. Now, we can also use the implicit differentiation to find the value of the second derivative at a given point. This is talking about the idea, and we'll discuss this more in Unit 5, the idea of concavity and the values of concavity, what happens with the second derivative, how that applies to the actual function. So for right now, we're just finding our second derivative value. So implicitly, we get negative 4y dy dx. 3 goes away, x becomes a 1. So dy dx would be a 1 over negative 4y. Now, if I want to take this derivative a second time, I'm not going to leave it in that format. I'm actually going to rewrite dy dx as negative 1/4 y to the negative first. Because now I'm not doing a quotient rule. Now I'm just doing a simple power rule. D squared y dx squared would be a positive 1/4 y to the negative second, or just simply 1 over, and then dy dx. Derivative y, you need to have a dy dx term there. So it's really 1 over 4y squared times dy dx, which is 1 over 4y squared times a 1 over negative 4y, so you get 1 over negative 16y cubed. So you might find certain scenarios where there's only a y left over, you're better off, rather than leaving it in the denominator, which is where it normally goes, because you're trying to solve for dy dx, you're going to have it connected to the y, so it's going to divide over. You write it as negative exponents. We could have done that in the previous problem, but we've just simply turned it into a product rule instead, which is fine, but at that point, might as well just do the quotient rule. Here, power rule versus quotient rule, oh yeah, definitely do a power rule. Now, they want us to find the value, so they give us the 0.11, so we just can substitute the 1 into y. And we get 1 over negative 16. The x value didn't matter. All right, so that's your implicit differentiation, find the value with the second derivative. All right, so that's it for Unit 2. So those are our different derivative rules applying to the basic polynomial functions. So in Unit 3, we're going to talk about the non-polynomial functions and their derivatives. We're going to talk about exponential functions, log functions, trig functions, and inverse trig functions. And then in general, a generic inverse function that's not inverse trig, just inverse function. And we'll use these different rules we talked about. We're going to use the chain rule for all those. We're going to talk about how to solve them with the product rule. We'll talk about how to solve them with the quotient rule. And we'll talk about how they can apply to an implicit differentiation. All right, so that's all of Unit 3, those special types of non-polynomials, which will refer back to this for those different rules. All right, as always, I appreciate you watching, and I'll see you next time.